Hello, my name is Roy Simpson. I'm a professor of mathematics from Cosumnes River College in Sacramento, California. In this video lecture, I'm continuing on in this lecture on using graphs to solve linear equations and inequalities. We're going to go into part B, which is using a graph to solve an equation or inequality. Now, I'm going to start this by telling you that normally you would need a graphing calculator or some type of exact graphing device to do this properly. This is not a standard method for solving equations, but it's a very unique, nice, interesting method. It also kind of links up the idea of graphing an equation and solving an equation. So let's go ahead and take a look at this. We're going to solve the equation 3x plus 1 is equal to 7, which is a particularly easy equation to solve normally, just by using algebraic methods. We'd subtract 1, divide by 3. But in this case, we're going to link up the idea of solving an equation and graphing an equation. So we're going to solve this equation by using the graph of y equals 3x plus 1. Really, when somebody hands you an equation, they're asking the following question. When is 3x plus 1 the same as 7? Or as I often say in class, when is 3x plus 1 the same height as 7? That's kind of how I say it when I teach a class. So the same height as 7. Oops, I spelled that. So let's go ahead and graph y equals 3x plus 1 by building a table of values. Here's the x values, the y values. When x is 0, just let x equal 0 here, you find out that y is equal to 1. When x is 1, you find out that y is equal to 3 times 1, which is 3, plus 1, which is 4. You could go on with this, but you only need 2 points really to graph a line, so that's all I'm going to use here. So let's go ahead and plot. Oops, that's not what I wanted to plot actually. Plot x equals 0, y equals 1, so I'll go ahead and plot that right here. And then we'll plot x equals 1, y equals 4. And at this point, I'm going to try to connect these dots as accurately as possible. Something like this. Now, I have this graphed out, and this is why, by the way, when I say as accurately as possible, this is why usually graphing by hand, doing this by hand is very, very difficult. It only works nicely if you have these pretty equations solving 3x plus 1 is equal to 7. But our question is, when is this equation of 3x plus 1, when is that equal to 7? In other words, when is the height equal to 7? So let me draw a little blue line here. Actually, maybe I'll make it a light blue line at a height of 7. So here's my light blue line at a height of 7. And you see that this red line intersects the height of 7, basically, when x is equal to 2. So the answer to this question is 2, actually. When is we want to solve 3x plus 1 is equal to 7? Well, that happens when x is equal to 2. And you can see, when x is 2, this line of 3x plus 1 turns into the height of 7. And I can even write down 2 comma 7 for the value of that point. So x is equal to 2. That's also why I stopped building that table after x equals 1, because I knew that when I hit x equals 2, I'd give you the answer. I didn't want that. So this is the idea of solving an equation using a graph. Now let's take a look at this next example. We're going to solve 1.82x minus 3.1 is equal to 5.5 by graphing. And we're going to go ahead and graph y equals 1.82x minus 3.1. And once I see all these decimals, I know I will not be able to graph this by hand exactly. So I need to use some other method. And the other method I'm going to use is using a graphing calculator. So let me bring up a graphing calculator here. Clear that out. I'll slide this over. This is a TI-83 Plus. And I'm just going to go ahead and graph. And maybe I should mention the keystrokes here because this might be the first time you've seen a graphing calculator used in a class. So maybe I'll show you what I'm doing. To graph using a graphing calculator, you usually have a button like a y equals button. This top menu of buttons here is always used for graphing. So I'm going to hit y equals, and it opens up a bunch of beginnings of equations. A y sub 1 equals, a y sub 2 equals. These just are different labels for equations that you can graph. You can graph a bunch, up to 7, even more at once. But I'm going to graph y equals 1.82, and now I need a variable x, and that will be this button right here. This is probably one of the most commonly used buttons on your graphing calculator. So I'll just put that x there. Minus 3.1. Now something I should mention here, that minus sign is used for subtraction. This sign right here is a negative sign. It's not used for subtraction. If you use that, you will get an error. Now let's go ahead and see what a graph of this looks like. I'm just going to hit the graph button just to see. Okay, well, it's a nice little line. That's great. But my question is, when is this line of 1.82x minus 3.1, when is that at a height of 5.5? So we want to know when we're at a height of 5.5. There's a few ways we could do this. One is to trace this out and get as close to 5.5 as possible. So if you hit the trace button, you'll see that a little blinking cursor appears there, and you can hit this right arrow and start going until you get to a height of roughly 5.5. The problem with this is that I'm going to pass up 5.5, right? See, my y value here is 5.4 and some change, and now I'm all of a sudden at 5.8 because it steps past that height of 5.5. So often using the trace button is not the best tactic. Another decent tactic is to look at a table of values. Once you have a graph, once you have an equation in under y equals here, you can technically look at a table of values for this. So notice right above this graph button there's a yellow word, and that word says table. So if I hit second, that second button allows me to access all the yellow words on this keyboard. If I hit that second, you see a little arrow blinks upwards. I'm going to access that table feature by just hitting the graph button there. And you can see, oh, all of a sudden it builds my table for me. Oh, this is great, right? When x is 0, y is negative 3.1. When x is 1, y is this. It's all based upon the equation you put in for y sub 1. You might say, well, let me see, can I type in a value here? What if I try to type in 5.5? Well, I'm trying to and nothing's happening. You can change that behavior if you want to, but it's a little advanced. It's not hard to do, but I think for right now it'd be best just to say, I just want to know how I can find out when this graph here is at a height of 5.5. Well, how about we just say we have one graph of this and I have a graph of 5.5 as well. I want to know when the graph of y sub 1, which is this, 1.82x minus 3.1, I want to know when that is the same as this other equation, 5.5. Now you might not know this, but that equation, y sub 2 equals 5.5, that is going to be a line as well. Here we go, let's graph it. Now do you see? You have two lines. This diagonal line here is the left-hand side of my equation. This horizontal line is a graph of the right-hand side of the equation, and I want to know when those two are the same. Well, aren't they the same when they intersect? So you can find out when they intersect. And to do this, you can use a very advanced feature on your calculator. It's under the Calc menu right here. It's the yellow words right above the trace button. Remember, whenever you want to access a yellow word on your keyboard, you'll hit the yellow button, which is the second button. Notice a little arrow comes up that says you've pressed the second button. And now I'll hit trace because that contains the yellow word calc. I want to go to the calculate menu, and I want to calculate an intersection. I want to know when they intersect each other, these two lines. So I'll go ahead and scroll on down here to option number 5. Now I didn't have to scroll, I could have actually hit the number 5, but scrolling down's okay as well. Once I get down there, I'll hit enter. And notice you have this little cursor. Let me go ahead and move it to the right so you can see it. You have a little cursor now, and it says, hey, you're on this first curve, 1.82x minus 3.1. Is this the first curve? Well, of course it is. I only have two curves, or two lines, so yes, so just hit enter. Now it says, hey, is this a second curve? Yeah, that's a second curve, absolutely. So I'll hit enter just to select that as my second curve. Now it says, hey, take a guess. It's actually asking me to take a guess. So what you're going to do is move that cursor over until you get close to where they intersect. You don't have to be that close, but just close enough, and hit enter. And it will calculate where they intersect. They intersect when the y value is 5.5, or in other words, at a height of 5.5. The input, or the x value, in other words, the solution to this equation, is 4.7252747. So I'm going to round that to the nearest hundredth and call that 4.73. So x equals 4.73. That's a lot to go through to solve this equation graphically, but it ties together the ideas of solving an equation and graphing an equation. It's much better when you look at an equation and go, oh, I'm being asked, when does this line equal this height of 5.5? That's really what it's asking. But often you'll just do this algebraically. So let's extend this concept slightly. Let's go ahead and use a graph to solve this inequality. Notice that it doesn't have an equal sign, so therefore it's an inequality. And we just want to know, when is the expression 1.82x minus 3.1 less than the expression 5.5? Or in other words, when is the graph of this lower than 5.5? Let me write that down. Now again, for this, we're going to go ahead and use the graphing calculator. Again, just turn this thing on. And again, I just actually have the old graph we just had up for the last example, right? We graphed 1.82x minus 3.1. We graphed 5.5. So when we hit graph, you see the horizontal graph here, the horizontal line, is a graph of 5.5. The diagonal line is the graph of 1.82x minus 3.1. And remember what we're asking here. We're asking, when is this graph, this line here, below the height of 5.5? Well, if you take a look at this, and maybe it would help if I maybe did a little screenshot here. So I set it off to the side. You could see that this graph is below the height of 5.5. Well, pretty much everywhere where I'm going to highlight. I'm going to highlight this in maybe a big, thick purple or something like that. So all these values right here, all the line along this along this edge, I guess, is all below the height of 5.5. So let's look at the x values that correspond to that. And I'm going to do that in a very fine red here. So if I go down here, I'll look at this x value. So basically from this x value all the way over in this direction, all those x values that I'm highlighting right here. In fact, I could grab the highlighter and do that. I'm thinking about it. All these x values right here. Whenever I plug in one of those x values, it leads to a y value on this line that is below 5.5. For example, when I plug in this x value right here, it leads to a y value down here on the line, which is definitely below that height of 5.5. If I plug in an x value here, it leads way down here somewhere. If I plug in an x value right here, it leads to this x value, but they're all below a height of 5.5. So again, it all just comes down to, well, I know it's going to be all these x values that I've highlighted, all these ones right here, all the way up to this x value, whatever that x value is. Well, let's find out what that x value is by just finding the intersection, which we did earlier, but I'm going to do it again just to kind of retell you how to do that. I want to access the calculate menu, so I hit the yellow button to access the yellow words. And then I want to find the intersection. I'll just select the number 5 here. It asks me, hey, where's the first curve? Well, I'm on the first curve right there. It says, is this your second curve? Yes, I am. I'll hit yes, it is, so I'll hit enter. And then it says take a guess. So I'll get really close to the intersection, take a guess. And it says they intersect at 4.73. So I'll go ahead and say this x value here is about 4.73. It's roughly that. It's not exactly that. So this means that for all these x values, all the way up to 4.73, all these x values are going to lead to outputs that are below the height of 5.5. Now, there are two types of notations you would use for this. You could either say x just has to be below 4.73, and that's actually a perfect notation. So as long as my x values, my inputs here, are below 4.73, all those highlighted areas, then I know that the height of the line is going to be below 5.5. There is another notation, it's called interval notation. This first one's called inequality notation. But the second one I'm going to show you is called interval notation. And essentially, you just are saying the lowest that this x interval can go down to is actually negative infinity. You can never touch negative infinity. So I'm going to write that. You can't touch it. It's just like MC Hammer. Can't touch this. Can't touch it. And then that interval, as I keep going forward, it grows until you get to 4.73, but it's never really going to touch 4.73 either. So it's also can't touch that end. But that would be called interval notation. Both are absolutely fine to use. One's just fancier than the other. Okay. So let's try this again with just one last example before we call it quits. We're going to solve 3x minus 43 is greater than or equal to positive 28. Let me switch to my fine pen here. So what I'm going to do is graph y equals 3x minus 43. And I want to know, when is that the same as y equals 28? So I'm going to graph those two things, those two equations, on my graphing calculator. And again, pretty much when you use this method, you're just going to use a graphing calculator. Let me clear that equation and clear this equation. In the first equation, I'm going to graph 3x minus 43. And in the second equation, I'll graph 28. And if I hit graph, you'll notice something here. Nothing happens. The reason why is because my window that I have is just not good enough. It's just, if you take a look at this, y equals 28, if you think about the last example we did, where we had y equals 5.5, that gave me a horizontal line at height 5.5. Well, this will then, just think about that pattern, this equation should give me a line at a height of 28. So this window, which goes from negative 10 to positive 10, and from negative 10 to positive 10 in both the x and y axes, this window is not big enough. We can adjust the window by hitting the window button and adjusting our lowest x values and our highest x values, and our lowest y values and our highest y values. So let's see. We said here that this will likely be a horizontal line at the height of 28, so let's make our highest y value be just 50. That might help out a little bit. And let's just go ahead. I like symmetry, so let's make our lowest y value be a negative 50. Now if you hit graph now, I see my diagonal line and I see my horizontal line. So this horizontal line must be y equals 28. That's the height of 28. This diagonal line right here that represents y equals 3x minus 43. That's the lower equation there. And I want to know where they meet. Well, they meet off to the right, which means I need my x values to be somewhat larger. So I'll go ahead and plug in an x value of, let's just plug in x equals 50. as my highest x value. Okay. And there we go. Very nice. The graph is kind of bulky and ugly, but that's okay. Now I'm going to go ahead and take a screenshot of this and paste it right on our screen right here. I'll kind of zoom in on it if I can. Boom, boom, boom. That might be a little large. Okay. So this question is really asking me to find out when this curve, this line, the diagonal line, when it is bigger than 28. So let me go ahead and highlight that on here. I want to know, in fact, maybe I'll use orange. I want to know when this line is at a height higher than 28. Remember 28 is this horizontal line. I want my line to be higher than that, so it's all these values right here. Okay, and on forever. So I'm going to go ahead and look down to the x-axis here and say it starts here, and then for every x value that's bigger than that, all these x values here, whenever I plug in one of these x values into that equation y equals 3x minus 43, it leads to a y value like way up above a height of 28. So if I plug in this x value, I hate when I do that. When I plug in this x value right here, it leads to a y value way up here. Next x value over leads to a y value way up there. So I see all these highlighted x values are what I'm interested in, and what I need to know is where do these two lines meet? I need to know this x value where they meet. So let's go ahead and use the intersect on our graphing calculator. So second trace, I'm going to choose option 5 for intersect. This is my first curve, this is my second curve, and I'll just get a little close to the intersection, hit enter, and it tells me it happens at 23.6 is when they both are at a height of 28. So 23.6 on forever. That's where they meet. And I know that the x values I want have to be bigger than that. But it turns out they can actually be equal to that too, because if x is equal to that, then, well, if I'm absolutely at 23.6 on forever, then I'm on the height of 28. And you see this equation here, or inequality, I'm sorry, is allowing me to be equal to 28. So that's absolutely fine. Okay. Now, if you were to solve this algebraically, you would get the same answer. If you know anything about solving this stuff algebraically, you would add 43 to both sides to get 3x is greater than or equal to, what is that, 60, 71? And then you would divide both sides by 3 to get x is greater than or equal to 71 thirds, which happens to be 23.6 on forever. Yes, it's much easier to actually solve this algebraically, but it's still very interesting to use the graph to solve this. So it does happen that it helps out sometimes, especially when you're dealing with stuff like quadratic inequalities later on in an intermediate algebra course, or polynomial inequalities, which happens quite often later on in a course.